talk about formalizing the meta theory of Lean. And so I'm going to start with some slightly outdated comments for a reason that I'll get to in a minute. So Lean is an open source interactive theorem prover developed by Lean at Microsoft Research once upon a time. There's a focus on sort of software verification and formalized mathematics, and it's based on dependent type theory, and that's sort of going to be the focus for today. So it's a classical theory. It's not homotopy type theory compatible, and it is similar to CIC or PCUIC, which is the axiom system used by Cook. Lean3 includes a powerful meta-programming infrastructure for Lean4Lean, and the mathlib library provides a broad range of pure mathematics tools for meta-programming.
Did you need to write Lean3 there?
I did. I'll get to that. I'm going to introduce the axioms of Lean in a few stages. So we'll start with the untyped lambda calculus. So this here we have an expression grammar which consists of variables, application, and this lambda operator. You can reduce on either side, and then you can perform this operation here, which is called beta reduction. So this was originally developed by Alonzo Church as a simple model of computation. It's equivalent to Turing machines. It has a primitive notion of bound variables and substitution, and there's this non-deterministic reduction operation because you can sort of perform beta reduxes anywhere in the term, which sort of simulates execution. In particular, the reduction is confluent. It satisfies this theorem called the Church-Rosser theorem, which says that if E reduces in n steps to E1 and to E2, then there exists some E prime such that they can both sort of come back together. This doesn't say that the reduction stops, but only that whenever you diverge, you can eventually come back together. We can add types to this by saying that we have some type T here on the lambda. And so here I've just given a very basic grammar of types. We have some type of individuals, iota, and then an arrow type which represents functions. So now these here are the typing rules. So this says that if x has type tau is a thing inside this context gamma, then we can derive it. And then this one says that an application is well typed if you apply a function to an argument of the right type. And then this is just a typing rule for lambda. And so in particular, in this calculus, all terms normalize. So we call this property strong normalization. Dependent type theory extends this by using a dependent type for this x. So now the second tau can refer to the variable x. We have to change the syntax, or the typing rule for application, and the typing rule for lambda very slightly. In order to have something interesting to talk about here, though, because otherwise, with this version, we don't actually have any way to put anything interesting in our types. So we need to have types as a thing to use, and so we added a type u that sort of tells us about our type. So we say that iota is a type, and this is the rule saying that for all is a type, and then the collection of all types is a type, right? So now we have this extended grammar where we've sort of stuffed the expressions and the types into the same syntactic category. So here they're separate, and here we've just stuck them together. And so this is, now we've really unified the two systems. So now everything is just talking about terms and types having this typing relation. So we don't need to talk about types being well-formed and terms being well-formed. Now it's all just instances of the same thing. We don't need, we only really needed this iota here just to make sure that our types was non-empty. And since we have u now, we can sort of deal with that. So there's a couple problems with this presentation. One of them is that type being in type was discovered to be inconsistent. This is known as Girard's paradox. And so the solution to this is to add a sort of hierarchy of universes. So you have the lowest universe, U0, and then that is it has a type, which is the next higher universe, U1, and so on. And we're going to have to attend to these universe levels also in the rule for the for all. So if you have something in type UM, and then this other type is in UN, then this will live in the max of the two universes. Now, we would like to use this, this typing mechanism also to encode propositions. So we will reuse arrow and for all as the logical operators, arrow and for all. That's actually why I've been writing them as arrow and for all here. So we can use them both as dependent function types, but also as the quantifier for all x some property holds. In particular, we would like to say things like all natural numbers are even or odd. We would like that to be a proposition. But if we used the rule that I gave on the previous slide, then we end up saying that this lives in U1, which is to say not propositions anymore. So we want them to collapse back into the land of propositions. And so we do that by modifying this typing rule slightly. Instead of saying it's the max of M and N, it's the Imax. What's Imax? Well, it's impredicative max. It's a function defined in this slightly funny way, where we say if n is 0, if the beta is 0, then Imax Mn is going to be 0 as well. And otherwise, it'll just be max like before. Okay, so now this is what our dependent type theory looks like. There's one more issue which we have to attend to, which is that we now have the ability to write reduction and the ability to write reduction sort of in our types. And so things won't sort of type check if we aren't careful. And the solution to that is to introduce a notion of convertibility, saying that if you have two types that are so-called definitionally equal, then if E has type alpha, and alpha and beta are definitionally equal, then E will also have type beta. And so here's some basic rules for how definitional equality should work. So we want a term to be related to itself. We want it to be an equivalence relation. We want it to be a congruence. We want it to sort of factor through all the operations. And then here we have two interesting rules. This one is called the beta rule. It says that we can apply lambda to an argument and then it substitutes into it. And this one is called the eta rule. It says that if you sort of form a function type, oh yes, this is a typo. This should say that E has a function type. So like for all A colon alpha beta, then if you construct a lambda like this and then apply it again, then you just get back the original function.
Mario? The solution?
I am presenting one particular approach to solving these problems, which by interesting coincidence lands us to Lean system.
Okay.
So we also want a framework for defining new inductive types, like the natural numbers. So I'm gonna say that we have this thing K. This is the syntactic category of, let's say, inductive specifications. And so 0 here just means an empty list. And C colon E says that a constructor called C is given type E. And then mu is a type operator which constructs the inductive type over that. And just to give you a sense of how this works, we'll say that the natural numbers are the inductive type T living in U1, which has two constructors called 0 and successor, where 0 has type T and successor goes from T to T. In addition to the mu, we also end up with C. This is the constructor, so that would be 0 and suck in this case, and rec, which is the recursor, which produces values of any type given an element of this inductive type.
Is this how it's implemented in Lean, that every constructor reference carries the entire definition of the type?
No. So in Lean, this is actually a sort of, it's a generative version of this. So here I'm writing sort of applicative version of inductive types where you just have some kind of type expression. But in actuality, in Lean you would have to write the inductive keyword, and then this is and then after that you write an inductive specification, and then it gives you a brand new type and some constants that mimic the behavior of these. But these are sort of equivalent modulo some aspects of tagging. Okay, and so here's some examples how we can construct exists and or true and false, and maybe that convinces you that this is somehow quite general and able to give you lots of interesting logical operators. And I think I said this already. So each inductive type comes with a constructor for each of the cases, and then also a recursor to prove theorems by induction, and also construct functions by recursion. And in fact, one of the aspects of propositions as types here is that these are actually the same operation from Lean's perspective. Induction and recursion are not really differentiated. And so the recursor for the natural numbers says this. So you can basically construct it based on the inductive specification. And we have some C here. This is called the motive. And it takes our type n into some universe ui for some I, for any I. In particular, it doesn't have to be related to the size of the natural numbers itself. So this could be eliminating into a higher universe. And then it takes one case for each of the constructors, and then it constructs a function out of n. Moreover, it has these rules regarding how it reduces. So this is some kind of analog of how the functions were reducing before. Now we're having recursors reduce when applied to constructors. Okay.
Mario, can you go back one slide? So I have two questions. The bottom, you're defining says p dot. What is this symbol?
We say mu of t in propositions.
Yes.
Oh yes, sorry, maybe I didn't define p. This is u0. So we're defining a mu over the universe 0, and then we just use the empty specification. So it has no constructors.
So since p is the universe 0, so there isn't any kind for the moment. There isn't any indices to your inductive.
This inductive has no indices. Yes, it lives in prop, and it's just
it's the bottom.
yeah, it's just
Then
false.
how would you input indices? So your p would be.
You mean like if you wanted to like here, if you wanted to define a parameterized inductive type where you have
That's a parameter, but I want some index, so I would like.
Oh, I see. Yes, so this doesn't have to be a universe, it can also be a telescope ending in a universe. And then
But we
in
don't
these
see
cases,
this.
you would apply that.
But we don't see this in this syntax.
Yeah, I said, so I said E over here, so I said mu x colon E. That E can be any expression, although there's a typing thing that says it has to be a telescope ending in a universe.
Thanks.
Okay. Okay, so yeah, so there are some rules on these inductive declarations to be sort of admissible. One of the more interesting ones is that it has to be strictly positive, and the short way to say that is that no t appears on the left side of an arrow. And so an example of this would be if I had t arrows 2, where 2 is like bool, to t, then this type, the recursion principle for it would imply a violation of Cantor's theorem, as you can prove that this type cannot exist. Or conversely, that if you were to add this as an admissible inductive type, then you would get a contradiction. Yeah, so you can also have inductive families. And EQ in particular is one of them. EQ equality on type alpha is defined with a parameter x and then it's a inductive family over the other argument of the equality, and then it only has one constructor, which says that equality holds of that x. And so you end up with this REFL x, and then the recursor becomes the principle of substitution.
Mario?
Yeah.
Is there rigorous documentation of how the recursors are generated in general?
Yes, so this is based on a paper by Debier, which was written, I don't know, 10 years ago or something like this, and called Inductive Families, and it was, yeah, I can send you a reference.
Is it implemented exactly as in the paper?
Not exactly.
Is there documentation of how it's implemented?
Stay tuned.
So nested and mutual inductives are extended into this?
Yeah, so there are no nested and mutual inductives at this point.
Okay.
Stay tuned.
There's a question at the back.
I was asking about nested.
Okay.
So this means T cannot be referring to a previously defined inductive, right?
T, yes, so you think of T as a bound variable in
Yeah.
this inductive definition, and it can be referred to here, and then it generates, and then the mu of it is the new type, and then it has certain properties that reflect substitution of this bound variable T with the type itself. And yeah, I'm not giving the full axiomatic thing, but it's in the paper if you're interested. Okay. So we also want to have this rule here which says that we want all proofs of a proposition to be treated as the same. And this is the way that you can write that formally, that if you have a proposition P and H and H prime are elements of P, then H and H prime are definitionally equal. And so this is it says that every equality has at most one proof, and so this is in contradiction with univalence. If you assume univalence and you assume this, then you can prove a contradiction, because H or TT.
I mean, you can still have hot and the universe of strict propositions.
If you have univalence for something to which this applies, then you can say that, like, univalence tells you that the equalities on a type are isomorphic to the isomorphisms of that type. So if you take, for instance, the equality from bool to itself, then univalence tells you that there are two elements of that equality type, and this tells you that there are one. So
Right.
if there are, there are restrictions on ways that you can set things up so that maybe it doesn't apply to this example, but that's an example.
What's anti-hot is the combination of a universe of strict propositions and an equality that's valued in strict propositions and is still able to eliminate intro types.
We can talk about this later. Okay, so we need to have a rule on inductives that are defined on propositions. So in this example, we have exists, which is supposed to, well, it will erase sort of the witness that goes into it because of this propositional irrelevance. Whenever you construct two elements of this exist, they are sort of made equal by proof of relevance, and because of that, we shouldn't be able to recover the value, or else we would have a sort of injective function that factors through equality. Well, yeah. So the solution to that is to have this recursor be restricted in this way. So this used to say ui, and now it says u0, and this means that it can only eliminate into other propositions. This property, so there are some inductive types, like equality, which do not have this restriction. We call them sub-singleton eliminators or large eliminating sub-singleton types, and they are special. Yes?
Those are inconsistent with hot.
Yeah.
Before you had dependent recursors, and this one is non-dependent? Because, I mean, if you go back, I would expect
yes.
exist implies user or something like this.
Yes, that's correct. So a dependent recursor for exists should say for all proofs of it would have it would have an argument of the type exists, and then it would say intro over here. And then this is just applying it to the two arguments. In the situation of proof, when you have proof of relevance and you're talking about a type like this, they are actually interderivable. So you can get the non-dependent one from the
This is the primitive one in logic.
this is not the primitive one in the logic. Actually, I should have written the other version.
So singleton elimination is also the dependent one, which is kind of
yes.
useless
Yeah,
because you don't have anything to work with.
Yeah. Okay. And then we have the sort of actual axioms. Question?
So which types exactly can't do large elimination?
So a proposition can large eliminate. So if it is not a proposition, then it can large eliminate. If it is a proposition, then if it has only one constructor, all of the arguments to that constructor are propositions, recursive arguments, or they appear directly in the indices of the target. Then it is large eliminating. In all other cases, it is not large eliminating. Yeah, it's a complicated condition, I know.
Intuitive reason? Why exactly?
Well, so the intuitive reason is that they sort of have one inhabitant by definition. There's only one way to construct the element. There's only one constructor. It's not taking any arguments that you could use to manipulate. Like in this case, it has only one constructor, but it's taking a value of type alpha. And so it really has multiple, clearly different inhabitants if you didn't do some kind of quotienting operation, which is sort of what you think of this as doing. So this one, you really need that quotient, but there are others like equality where there's only one refle. There's only one way to construct the inhabitant of it, and that's sort of the motivation for saying that actually you don't lose, like it's not inconsistent to be able to recurse into the higher universes as well. But like this one, if you could recurse into higher universes, it would be inconsistent. And so another way you could think of it is like, this is some syntactic criterion that we know how to prove it doesn't introduce inconsistency. Okay, so there are three actual axioms. These are propositional extensionality that says that if you have two elements of prop and you can prove if and only if for them, so one implies the other and vice versa, then they are equal. You can think of this as sort of univalence for propositions. It implies, in conjunction with the other things, that the prop type has only two elements, like exactly two elements, and one is true and one is false. Quotient types are given this axiomatization here. So they are basically, you give an equivalence relation, and you get like a make function that constructs elements of this quotient, lift, which takes things out as long as they preserve the equivalence relation, and then sound tells you that if the relation holds, then they are then mapping them into the quotient makes them equal, and then you also get this computation rule. You can actually construct quotient types if you want everything except for the definitional equality. You can actually construct them without the axioms. You can just use some sort of classical like ZFC techniques in order to do it. But if you want the full thing, then you have to axiomatize.
Where do you say that it's an equivalence relation? I see a relation.
Excellent point. So this is actually doing a quotient by an arbitrary relation. You might ask, well, what does that even mean? What this is actually doing is quotienting by the equivalence relation generated by the relation you give it. And it turns out that these rules are exactly what you want. Like in this case, you say, oh, if R holds, then it's true. Well, then that means on all things generated by the equivalence relation, this will also be true, so this still works. And then similarly, sound, you can beef up the sound, you can prove the extended version that says for all x and y in the equivalence relation generated by R, and then this also holds.
So you're saying the symmetric transitive closure of the relation?
Yes, reflexive symmetric.
Reflective symmetric transitive closure. Okay.
Yes. And then the final rule is the axiom of choice, and this really turns Lean into a classical theory. And the way this is stated is in a particularly strong form, sometimes known as global choice. We can define this thing non-empty alpha, which is just an inductive type with one element, or with one constructor, give intro of alpha, that's a typo, I think it should be intro alpha arrows t. So you have alpha arrows t, and then it's in U0, prop, so that means this is sort of like the propositional truncation of the original type alpha. And then choice says that you can go the other way, that like if you have an element of non-empty alpha, then you can get an element of alpha. By the way, another way you can read this is as exists x colon a such that true. So just mere existence of an element of alpha. Question?
Can't you derive things for quotient types from the axiom of choice?
You can, again, you can prove everything except for this. You can't derive the computation rule. Yeah. Okay, so I'm going to start speeding up. So one of the interesting properties of the type system is undecidability. So this is sort of one negative property of the type system. There's a interaction between subsingleton elimination and proof irrelevance, which means that you can do some construction, say that you have some recursion over this funny inductive type ACK, defined over ACK of greater. So ACK says that a relation is well-founded. We're applying it to the relation of being greater than on the natural numbers. Greater than is not well-founded on the natural numbers. However, you can put such a variable in your context anyway, and when you are in that context, definitional equality just breaks down. You get the ability to compute things by recursion, even though the recursion is sort of not well-founded, and this is a sort of example of using that to decide the halting problem using a definitional equality. And you can lift this to definitional equality even not in inconsistent contexts by using lambda, basically. And so in actuality, Lean resolves this by under-approximating the judgment. It regains decidability and it loses transitivity instead. And you also lose subject reduction. In practice, this is not a big issue, and it mainly shows up in the realm of like things taking too long if you unfold too many things, which was sort of already a problem for other reasons. So Lean has a model in ZFC. There's a sort of obvious model where we treat types as sets and elements as the elements of the sets. I won't go into the details of the argument here, but we can talk about it afterwards if you're interested. And here's a statement of the sound theorem. So it says that if, like 3 says that if you have a typing relation, E has type alpha, then if there are k inaccessible cardinals, then the interpretation of E lies in the interpretation of alpha. And so this is a slightly, there's some complications here to make the statement slightly stronger so that we can prove this theorem here that says Lean is equiconsistent with the theory ZFC with there are n inaccessibles, where you put in this axiom for all n's less than infinity, or less than omega. So that is to say, within this axiom system, you know that there's 42 inaccessibles, but you can't prove that there are omega many inaccessibles because you would need an infinitely long proof and grab all of those axioms together. And this reflects something about how Lean can only use fixed layers of that universe hierarchy. It's not able to quantify over the whole thing at once.
Can you please explain too? That level gamma derives alpha?
So this is saying that, so level is describing the universe level of a type. So the level alpha equals 0 is saying that alpha is in prop, right? And this dot is like the proof element or the unique element of true. I mentioned that like propositions are a two-element type and so on. There's one interesting property that I'll get back to in a bit, which is called unique typing. So if E has two types, alpha and beta, then those types are definitionally equal. You get also these definitional inversion rules that says that if UM is definitionally equal to UN, then M and N are equal. If two for all types then are definitionally equal, then their parts are, and so on. These all look very reasonable, and Lean will agree when you ask, are these definitionally equal? It will say, of course not, one of them is a universe and one of them is not, right? But proving this with the idealized one, which is transitive and so on, is actually quite difficult because the definitional equality can go use transitivity to go through lots of larger proofs and so on. And so this is actually the majority of the technical content of the proof. Okay. This is not true on the nose in Koch because of universe cumulativity. So you could have a term that has two types, but one of them will only be in some kind of cumulativity relation with respect to the other. So I believe there are more complex versions of this statement, but it's complicated. And I'll skip the explanation of the proof. Yes. Okay, so possible future work includes more model theory of Lean, for instance, proving unprovability of this equality, this double equals a heterogeneous equality, or figure out how the VM evaluation model relates to the Lean reduction relation. Maybe we can prove strong normalization, and maybe we can formalize the present results here in Lean. 5 years later, I came back on this. This presentation was given to my master's thesis committee, and this was my type theory of Lean paper. This paper is now a standard reference, which is nice. The model theory of Lean, as I mentioned on that slide, was still not formalized, but the main results are now sort of common knowledge. There's these two main models, the cardinality model and the this sort of tagging model where you make lots of types different or you make lots of types equal, and it helps to understand the structure of when can Lean prove things equal or not. The question I asked about VM reduction is still open, although there are some interesting results of this done in Koch. Strong normalization has been disproved. So there's this paper here by Abel and Coquin that show that proof of relevance actually allows you to construct sort of untyped lambda calculus inside the world of reduction of proofs. And you might think, well, why would you ever want to reduce inside proofs? Well, it comes up during the reduction for the accessibility relation that I showed from before. So sub-singleton elimination causes this behavior of having to reduce a proof, and when you reduce a proof, the reduction now is known to potentially not halt, and so strong normalization for Lean is false. So what I want to present now is the formalization of all of the results that I was just talking about in Lean.
So weak normalization holds?
Weak normalization also fails, as far as I'm aware. I need to double check the exact statement, but I'm pretty sure it's also false. Okay, so Lean4 is about 80% written in Lean. That includes the parser, the elaborator, the tactic language, the metaprogramming framework, and the LSP server. The exceptions to like what is left, you know, there's this picture of all the languages that are used in the Lean4 repo, and you can see that Lean is taking over. The exceptions are the runtime. Well, so the runtime is quite difficult to write a programming language that doesn't have a runtime. So that's probably not going to be written in Lean for the foreseeable future. The interpreter, it has some high performance requirements. It's not clear whether it would be worthwhile to rewrite it in Lean. About half of the back end of the old compiler. There's some weird historical happenstance involved in these bits here and the kernel. Now, of these, one of these is both mathematically interesting and soundness critical. So maybe we should think a little bit about implementing this in Lean. So the project goals for Lean4Lean are to make a Lean kernel, which is complete for everything that can be handled by the original Lean kernel. And also that it's actually competitive, that it is actually usable as a kernel to apply to systems in practice so that it can be considered as a replacement for the original kernel. Then I want to write down the type theory of Lean, but formally, this time in Lean itself, prove some structural properties about the type system, like the ones I showed before, and then prove the correctness of the implementation with respect to the specification. Now, the status of these roughly look like this. So, made a Lean kernel. It is complete. It is competitive. We wrote down the type theory of Lean. The structural properties about the type system are sort of work in progress. I'll tell you more. And proving the correctness of the implementation has mostly not been started yet. So the kernel is sort of a carbon copy of the C++ code. It does all of the same fancy tricks as the original and all of the same dumb ideas as the original. So it has union find, data structures for caching, caches everywhere, pointer equality testing, bidirectional type checking, nested inductive types, mutual inductive types, EDA for structures. These are features that didn't even exist in Lean 3 and did not exist in my paper. In addition, a naive implementation of substitution and reduction. I read an X here, but this is the same X as it exists in the actual kernel. So it is replicating the behavior.
So, a small question, is the Lean code much shorter than the C++?
The Lean code is much shorter than the C++ code, yes.
What's the factor?
It is probably about 2x. Not a huge amount, but it was, yeah. So I would say it's suitable for differential fuzzing. That is to say, it will get like exactly the same counts when you watch, when it does it go left, does it go right, what does it reduce, that sort of thing. You can see it do exactly the same things. This is valuable because if and when we ever prove the consistency or the correctness of this version of the kernel, it might mean that even if we keep the original C++ kernel, we now have strong evidence that the original one is also doing the right things because they are so similar. It also uses Lean's own expert type, so it's really reusing as much as it can of the sort of Lean ecosystem and connecting itself, reusing the environment and so on. And in a couple cases, not too many, mostly because they weren't actually available in Lean, but some portions of like the algorithms were reused when they were already written as Lean functions. One unexpected benefit of this that I didn't list on the sort of project goals is that people immediately started getting interested in hacking on it, and this is sort of really cool. Like I wanted, one of the things that writing it in Lean helps with is that, there's all of these people who are using Lean and getting interested in this stuff, and it's a lot easier, it's more approachable to have a kernel like this written as a Lean function rather than written as some C++ code and this like soundness critical, no one ever goes there be dragons kind of thing. And so I have two examples here. David Renshaw made this lovely YouTube video that you should all watch, talking about exploring a certain reduction trace, like some reduction problem was blowing up, and he was able to use Lean4Lean to visualize what was happening. And then Rishikesh Vaishnav showed Lean4Less just yesterday, and so for the people watching, you should watch that video as well, which is about using a modified version of Lean4Lean in order to perform extensional to intentional type theory tricks. Here's some stats from the paper. So Lean, this is checking. So Lean4Export is basically you run the original C++ kernel, and Lean4Lean has exactly the same interface. You are just using the other kernel this time, and you can see about a 30% degradation with respect to the original. So whether you think this is a good number or a bad number depends on your disposition. I think that that could be better, but probably making it better will involve improvements to the actual Lean compiler. You know, this is written as Lean monadic code, blah, 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 and so there's a bunch of things that the compiler has to do right, and competing with C++ is difficult. Lean itself, when it went through that original phase, Lean 3 was mostly written in C++, Lean 4 is almost entirely written in Lean, as we saw, and this was, I would say, worth it. I think the devs would agree that this was worth it for being able to improve the extensibility and the sort of development features that were added by moving to this sort of more dynamic framework. And it has since clawed back all of that performance and quite a bit more. Lean 3 was taking, 6 hours to compile mathlib. It's now taking like 1 hour. This is because of algorithmic improvements that were made possible by making it easier to write the kernel itself, or the system.
And would you say it was a mistake to start in C++ in the first place?
Leo is a C++ developer. He grew up, writing this stuff. He did Z3 before this, and he has personal familiarity with C++. I don't begrudge anyone using the languages that they are efficient at using. And I mean, C++ does have many advantages for being able to write high-performance code, and a proof assistant is a high-performance piece of software. So I think there are good reasons to use C++, but there are also good reasons not to, right? And so this is sort of a decision for the devs, I would say.
It would seem like getting the algorithms right ended up being more important than having a fast programming language. Would you confirm it?
Well, yes. I mean, to the extent that you can establish the correctness of the system, this is writing in a functional programming language can make it a lot easier to argue for the correctness of the system. But keep in mind, Lean has no plans of verifying the majority of the software, right? That is not in the works. I am planning to verify a small portion of it, a very important small portion of the software, and this already is quite a large project. Okay, and yeah, so like one of these examples of better algorithms, I want to experiment with better reduction strategies. The reduction strategy, as I mentioned, is quite naive, and I think it's holding back some kinds of usage of Lean, and this is never going to happen with the current kernel. We really need a better one. Okay, so back to type theory of Lean. So here's the sort of new and improved version of the typing rules that so this is actually a copy and paste from the Lean code and translate to LaTeX version of the typing rule. One of the key differences is this is Lean4. This is Lean4Lean's model of what Lean4 ought to be doing. So we have now a sort of combined definitional equality and typing judgment. Both versions of this kind of typing relation appear in the literature, and it's still sort of unclear which one is going to be easier for proving theorems. I think, let's see, as far as rules, these are mostly the uninteresting ones. Okay, so here we have definitional equality for all application, the conversion rule again, the beta rule, the eta rule, which we saw before, proof of relevance is exactly the same, and then we have this extra. I'll get to the extra in a bit, but basically this is saying we add additional definition. So you read this here as saying that we have something in the environment that tells us that two terms ini prime, which are closed terms, are definitional equal to type alpha, and then we can sort of instantiate that sort of. So this is basically a simplified version of it where we just say you have some definitional qualities that have been added to the system in addition to the usual dependent type theory stuff. And I said this already. So theorems. These are all boring theorems. So this is weakening. This is substitution. This is also substitution. Oh, this is substitution of levels. This is substitution of expressions. And this is something like the cut. Oh no, this is saying that you can replace something definitionally equal in the context. So this is actually quite a useful rule. We also have like inversion rules. So this says that if you can derive that a for all type has any type at all, it doesn't really matter what it is, then sort of the inputs to the for all rule hold for it. And this you can just prove by induction. So here's some slightly more interesting theorems. So this, if you have a typing relation, then the type itself is well formed. Also there's a slight variation on substitution, where now we've changed the A, so now instead of just having A, we have A and A prime, which are definitionally equal. And this one, it's not quite obvious how you prove this one, because you sort of recursively have to know that it holds in order to get pieces on the right to type check. And now we have some conjectures. So earlier I showed you the same slide here, but with the word theorem, but I've had to remove the word theorem because while formalizing these proofs, I found a gap in the proof. I still believe that these theorems are true, but the formalization process is no longer just a mere clerical work, typing in the proof as we go, and so some discovery is happening here. There is an alternative path to this sort of proof of soundness that does not depend on this unique typing theorem, but some of the kernel optimizations depend on this theorem. And remember again, these are the really obvious ones, the ones that, Lean, if you ask Lean, is a universe the same as a pi? We'll say no, and everyone would agree that that's a reasonable answer.
But question, didn't you say that you miss subject reduction? Isn't that going to cause trouble?
I should mention the failure of subject reduction happens for the algorithmic typing judgment. This here, this equality, this is the sort of idealized version which closes under the rules of the typing system, rather than the sort of under approximation that Lean is actually checking. We're sort of only going for soundness here, not completeness. So sometimes Lean will say that things are not well typed when they are in fact well typed. Yeah, so here we're trying to put some kind of upper bound on the sorts of, we do not want the definitional equality relation to say that every two terms are equal, because then things start to break down. And you can't prove these using the model either, because the model of ZFC, the model of Lean and ZFC is an extensional model. It can't differentiate between the definitional equality and just propositional equality. So that means, for instance, if you're in an inconsistent context, then there's no way that you can prove this kind of theorem, because everything's equal. So here's a sneak peek at a couple recent results. I gave these, well, I skipped over the slides that gave the definitions here. So this subscript P equality, this is like a simplified version of definitional equality that only uses eta and proof of relevance. And then we have two notions of reduction. These are proof artifacts, just to be clear. These are being used as steps in a proof of this. So we want to say that if you have a definitional equality, then you can reduce both of the two sides to the point where they now hold by this P equivalence relation. The P equivalence relation is very syntactic, and it's easy to see, for instance, that universe and pi are not in this relation. So this is sort of the key to being able to prove all of those theorems that I showed before. And so the status of this, I managed to prove this just last week. I was stuck on this for like 5 months, so I'm very happy that things are, for a while I was worried whether the theorem might not even be true, right? But now I think things are starting to get going again. And this second one is called the triangle lemma. I'm like 80% done with this one, and it doesn't look that bad yet. And then Church-Rosser is this middle one, and it's a combination of basically these two lemmas and one other lemma. Then we'll sort of have the core of this proof that the definitional equality relation is sane. And the hard part, well, the next unsolved part of this is sort of figuring out the recursion structure, because actually all of these theorems rely on a lot of properties of the typing judgment, including this property, right? So a lot of the challenge in structuring this is figuring out sort of where to start your induction proof such that things are decreasing in the right way, because everything is so mutual and tied up with itself. So I'm still hopeful that let's say once the main part of the proof is done, it'll be easier to sort of analyze the things that went into the proof and hopefully get a reducing metric out of it. So inductive types, they're kind of stuffed into this T extra rule, right? So I just said, like, you add definitional qualities to the environment, but doing this in general gets you a really crazy system. So you have to restrain what kind of definitional qualities you have. Certainly, if you want to prove these theorems, you really need to understand what's in that reduction relation. So I'm experimenting with ways to make this sort of reduction, this inductive definition just more manageable. So this is what like the definition of one of these cases looked like. And I mean, it's sort of hiding a lot of complexity here. Like C, E, P, and H are all n-ary, you know, they're telescopes. They have a whole bunch of arguments. And V isn't even written on the slide here. V is like some big lambda involving a bunch of the other terms, and is defined by recursion over the inductive specifications. There's quite a lot of complexity that goes into here. And so I'm trying to see whether I can do some kind of simplified pattern language that would allow me to describe abstractly the shape of this reduction rule. One of the things that came up in Rishikesh's talk was that the reduction rules sometimes need to have side conditions. That's this psi here. So here we have, you want to think of, we added to the environment something that says P, so P is like a pattern that's going to match a term, and R is what it's going to be replaced by. And we want to say that P will reduce to R if psi, some condition, holds. And here we're going to say, okay, if E matches this pattern P, and then if psi holds, and all of the subterms reduce, then E reduces. So this is sort of the standard form of this parallel reduction applied to this, this family of cases. And this family is sufficiently broad as to cover the quotient rule and also all of the different varieties of inductive type. And so this psi here is just a conjunction of definitional qualities over the right-hand side, or over expressions written in terms of the variables. Okay, so you can use Lean4Lean as a replacement for Lean's kernel today. It's working, it's quite efficient. If you would like to use it for that purpose, that's great. The formalization, as you've seen, is still under active development. There's still a lot of questions and you know, half-finished proofs. And so not just the formalization, but also the mathematics is still sort of evolving. The way I would sort of summarize why this is difficult or complicated is that confluence independent type theories is a hard problem. I've looked around at like Koch and Agda, they both have versions of this, and they both said, we make the reduction not depend on typing because it makes things easier. And I agree, it does make things easier. Unfortunately, Lean really goes full on with the typing. It's needed for several things that are absolutely essential to the way that Lean works. And so we can't hack around it. We really have to use it directly. And I mean, there's like a half dozen people that have been working on Metacock for like a couple of years. But Lean, it's just sort of yours truly. If you identify as a type theorist, then please come and help us out build this Lean4Lean system. Thank you.